Hi, welcome to Physics 2211, Lab 1 on constant velocity. My name is Maria Jyotish, and let's get started. The purpose of this lab was to observe the motion of some object moving at the same speed without changing direction, and then to construct a computational model based on physics principles which we can compare our observed data to. Some fundamental physics principles and models we can see in this lab are Newton's second law, the momentum principle, which relates the net interaction between the system and its surroundings to the observed motion. We also see in our observational model that the net force, the sum of all forces, may be impacted by the presence of friction or other forces, whereas in our computational model we will see the net force is equal to zero as no other force impacts the object after the applied force. And for a brief preview, the two models, observed and computational, will show the slight impact of external forces causing the discrepancy between their data. As stated earlier, the purpose of this lab is to observe an object at constant velocity, which means the net force on the object should be zero. Since our lab isn't in an ideal world, you'll notice that our observed data's net force will not be zero since there will be external forces acting on it. Our computational model, however, applies Newton's second law, as there will be no applied or frictional force, therefore no net force, and constant velocity. The position and velocity update formulas are used to create our computational model. Here is a video of our observed object, the system being the marble and the surroundings being everything else. I used Tracker to analyze the motion of our marble, and as you can see in this position versus time graph, which plots the data points as the object moves, that the trend of this line is downwards and linear, which implies that the velocity is negative because the marble is traveling left of the y-axis over here. Next, I used GlowScript to create a computational model of an object moving at constant velocity with similar parameters to my observed object. First, you can see I changed the ball mass to closely match the mass of an average marble. Next, I updated the ball's initial position to match the initial position of the marble in the observational data. Then, I plugged in -0.3 as the constant velocity, which I got by taking the average velocity of two data points from my observational data. I also updated delta t to match the frames of our video. Now down here in our loop, you can see that our net force is set to 0 to maintain constant velocity. Also, as mentioned before, our position update formula and velocity update formula are used to plot each data point as time passes in delta t increments. Next, taking the observational and computational data, I used Excel to create a position versus time graph to compare the results. You can see here that initially both data sets aligned, but then later began to diverge. This is most probably due to the frictional force acting on our object causing it to slow down and not cover as much distance as the object in our computational model, which has no net force and thus will always travel at the same velocity unless acted on by another force. To improve our observed data, we would try to observe an object moving at constant velocity on a surface with minimal friction. Some follow-up questions to this lab are, what if we had set the direction of our marble to be going, in our case, the positive x direction? Well, in that case, all that would change would be the slope, in other words velocity, of our graph, to be positive, which would result in an upward linear line. However, this wouldn't change the result of our observational data slowing down and covering less distance, as there would still be external forces acting on it. Now, for the question, what does it mean? As mentioned before, we set the net force in our computational model to be 0. However, it is unknown whether the net force was actually 0 in our observed data, as there could have been many pushes, like a slope downward, or pulls like the frictional force that affected the object's velocity. It's hard to say how many pushes and pulls there were impacting our object, in our observed data, as you can't really see them. That concludes my Lab 1 results, and thank you for watching.